My project title was Latent and Artificial Neurons. I'm working under Dr. Brian Kelleher. And what we're going to do is we're going to see some neural looking excitability in quantum dot lengtheners that aren't predicted by our current lengthener rate equations. We're going to fix those equations, see what's happening, and then show that what's happening is qualitatively at least, the exact same as one of the most basic and widely employed models of neuron excitability, the Fitzhugh-Nagumo model. Before we can get there, though, I want to bring everyone up to speed. So in case you don't know how a lengthener works, what we do is we have a special material, which could be a variety of things, a semiconductor or some sort of gas, or even quantum dots. And we're going to be able to excite electrons in this, roughly speaking, to an excited state. And so we know that if they fall back down with spontaneous emission, they'll release a photon. But in a laser, what we do is we find that if we send in some light here with some frequency, that it's going to help encourage the excited electron, which we now call a carrier, to fall down. And the photon we send through comes out fine. But the photon that's released actually matches the direction and the frequency of the guy we sent in. So we get a very coherent beam of photons here. And this is stimulated emission. And it's actually what SE stands for in the word laser. So how do we get this light coming in? And in our setup, we're injecting the light here with another laser. So we're going to be looking at what happens to the secondary laser in our equations, which is receiving light from some primary laser that's being run at some sort of fixed frequency. And our equations look like this. So try not to get overwhelmed. They're not important to try and decipher what's going on just by looking at them. You won't be able to. And you can see what it describes are, if we give some initial conditions, how the field amplitude of our secondary laser changes. And just to note, the intensity is going to be R squared. So I like to think of R as the brightness of the laser, but that's obviously wrong. But just if you want to think of it like that. Phi is going to be our phase difference, and N is the carrier density in our secondary laser. So the important parameters here that we can physically change are K, the injection rate, so I can change how much light I'm injecting. And I can also change the characteristic frequencies of my lasers, and the difference in those is called the detuning. Alpha, we're going to set at 2 for quantum dot lasers, and P, we're going to leave at 0.5 for now, but we'll come back to that later. I haven't told you what tau is, and it's the ratio of photon lifetime to carrier lifetime. So indulge me. If the carrier lifetime were really long, that would mean that our electrons are staying up in that excited state for really long. And so what might happen is we might run out of carriers to excite. The intensity of the laser might dip, so R might go down. And then a bunch of carriers might fall down then, which will make our intensity go up. And we get this sort of energy being transferred between the carrier and the intensity of our laser beam. And these relaxation oscillations is what they're called. It turns out if they're small enough to not matter, we can just take the class A limit, which for a class A limit means the carrier lifetime is really short. So we never run out of carrier and tau gets big. So if I divide across by tau here, I have this equation equal to approximately 0. I solve for n, adiabatically eliminate it, and it's gone. We never need to see it again. And so here are the class A laser equations for optical injection. Now what usually happens in optical injection, as long as you have a high enough injection rate and your detuning is not too big, is you'll get injection locking, where your secondary laser couples to the primary laser and locks onto a phase and an amplitude. So in these equations, by eliminating n, we actually create a region of bistability, which means that depending on what our initial conditions are, these equations might lock onto a higher amplitude or a lower amplitude. So the question is, do we see this in quantum dot lasers? Do we have this bistable region? And it turns out we do, but we have some other stuff too. And one of those other things is this spiking, okay? Quite interesting. So it looks like what's happening is I'm jumping from my lower amplitude locking to my higher amplitude locking with a fixed period. And you can check out this paper here if you want proof that this is really, really periodic. It's not noise induced at all. So to fix our equations, which don't have this behavior in them, they just have the bistability at the moment, we're going to introduce optothermal coupling. And optothermal coupling just means we're going to consider temperature now. What does temperature do to these equations? Well, we know that if we increase the temperature of a laser, its characteristic frequency changes, and so the detuning should change. And so we define this new parameter omega that we're throwing back into our equation to be the change in detuning due to thermal effects. And that's captured with this guy here. So the detuning is changed by omega. And the thermal effects are going to kick in when our laser heats up. And our laser should heat up when our intensity or our field amplitude is really big. So let's plug in the bistable region parameter, see what happens. I should probably tell you what C is. So this is how coupled the thermal effects are to our laser. We're going to leave that at 0.1. And because thermal effects are much slower, at least, than how R and phi change, this gamma here is going to be small. And this will be important later. So plugging in our parameters, we get what we want, like here's the spiking between our bistable points. And this is all due to this omega here. So, naively, we were right. If you want to compare it to the experimental graph, here you go. Looks pretty good to me. So we could finish here and say we're correct in everything, but we really need to figure out what's going on. So in my three-dimensional equations, I can plot how they evolve in 3D. And it looks kind of weird, and it doesn't really tell us what's going on physically here. You can see I start off somewhere, I zip over to the far corner, and then I get stuck in a loop. And this apparently is causing the spiking. So when do we even get the spiking is a good question. So this is a bifurcation diagram where I'm varying delta and k, the parameters I can physically change. And what we find is as long as I'm picking delta and k from in this loop here, I get bistability and I get the spiking region, or I get the spiking between the two stable fixed points, right? My laser is locking onto some point and then very quickly locking onto the other and going between the two. In these other regions, we get some crazier behavior that we'll see at the end. But for now, this diagram's useless. It's obviously really crazy. The colors are just, mind-blowing. These codimension 2 bifurcations are complicated enough without having about 7 of them. So we're going to use some approximations, 2 of them in fact. So take our equation here. Remember now that our gamma is quite small. And so our first approximation is going to be the fast subsystem, where R dot and phi dot are much greater than omega dot. They're dominating the change in the system. And so what I can say is that omega dot is roughly 0, right? Gamma is effectively 0 here. So omega is a constant in our fast subsystem. The other approximation we're going to use is the slow subsystem, where R and phi finally lock on, they hit a fixed point, and they stop changing. So now these are roughly 0, and omega is the only thing changing the system. So if we look at the fast subsystem, I have a plot here of R versus omega, and omega dot is now 0. So if I think about what's going to happen, what I've drawn here in this line means that if we start off at a point, let's say here, omega is fixed in our fast subsystem, so we can only move vertically. This line here indicates it's a fixed point. So my laser for this value of omega is going to lock on to this amplitude here. If I had an omega over here, let's say, well, we actually get two stable fixed points and one unstable fixed point. And this is our bistability. So if I start off here, I'm going to lock on to this lower branch fixed point. And if I start off in this region, I'm going to lock on to my higher amplitude. So that's all well and good. We understand what the fast subsystem does. It's going to snap us onto these lines. So the slow system now, to understand it, we draw this line here. And this is the line omega dot equals 0, the omega null line. And it breaks our plot into two regions, where omega dot is where omega is increasing and where omega is decreasing. So this tells me if I'm at a fixed point here, or and phi aren't changing. The only thing that's changing is omega, and it should push me to the right because omega is increasing. And if I'm down here on this fixed point, I should get pushed to the left. So let's combine these fast and slow subsystems, see what an actual trajectory looks like when we get this spiking behavior. And it looks like this. All right, blink and you might miss it, but the fast subsystem starts us off here and snaps us immediately up here. We start moving right, and we drop down onto the lower branch. We start moving left, and slowly but surely, the slow subsystem is going to push us until all of a sudden we lose the lower stability of our injection locking, and we are forced to lock onto the higher amplitude. Rinse and repeat. So if you follow what Orr's doing here, you'll understand why we get this spiking. So Orr's moving slowly, slowly decreasing until we spike downwards, and then it's slowly increasing until we spike upwards. Now, it's time to talk about neuron models, now that we understand what's happening in our laser system. The Fitzhugh-Nagumo model is very basic. You have the equations up here, but it is actually a simplification of the four-dimensional Hodgkin-Huxley model, which won a Nobel Prize. So we're doing, good neuroscience here. This is a great model, and it captures sort of the action potential of a neuron. If I slowly vary I can actually get huge voltage excursions and this sort of spiking behavior. These are really easy to analyze as equations. You only need a small background in nonlinear dynamics. And the phase plane actually looks like this. And this is surprisingly similar to something we just looked at. So, really, if it walks like a Fitzhugh-Nagumo and talks like a Fitzhugh-Nagumo, chances are we're dealing with a Fitzhugh-Nagumo. So let's take our laser equations once again, see what we can do with them. What we're going to do is we're going to lower P, and I'll justify this in a second. Now, if you imagine lowering P, you can get that the numerator here will dominate the behavior compared to the denominator, because this will stay close to 1 for low R, and this will be the dominating change. So apply that approximation. P, remember what the pumping current above the threshold. Sorry, I didn't expect anyone to remember that. Do that. And now we're going to use some trickery. We're going to just rescale time, rescale a few parameters, and get our equations looking like this. And so really, physically, what are we doing when we lower P? Well, if I have a low pumping current, remember our levels here with the electrons. As I pump current in, I'm going to excite electrons up. And if I excite too many electrons, of course, I'm going to get those relaxation oscillations. So for low pumping current, I'm kind of not going to ever run out of carriers. So essentially, our relaxation oscillations don't matter even more. And so our choice to move to the class A system is just more grounded. And so the bistable region should definitely exist. And just comparing everything we've looked at now so far, here's our class A equation with the optothermal coupling simplified down. Here's our Fitzhugh-Nagumo. And They look pretty similar, except for this guy in Fitsunagumo and this guy in our Laker equation. But really what's happening in all this guy's doing is it's going to lower I as the slow variable increases. And this guy here, because of how phi is, it's just a function of or and omega, it's going to lower k as the slow variable changes. So roughly the same behavior as long as you're careful about your initial conditions and your gamma here. And so really, I'd like to finish up there. I have a few more animations of some other regions. And the future prospects of this are basically that there's other types of neural excitability, and there's other parts of our Laker equations that we haven't looked at by focusing on this loop. So there's more work to be done here, maybe combining with the work Jack did. And just thanks to everyone, including Dr. Brian Carroll, of course, and I'm happy to take any questions now.
Thanks a lot, Adam. Okay, folks, Adam is available for questions. Okay, Andreas, thank you.
Just a very simple question. What was the most difficult thing in the project?
The most difficult thing, I would say it would be making this bifurcation diagram here, the full thing. So the initial software I was using was Auto, part of XPP Auth. And I was having some trouble with my laptop. I think it's just not good enough. I wasn't able to make the numeric small enough to catch a lot of the codimension 2 bifurcations. You know, they're nasty little things, really. So I bought MATLAB and installed a package called MatCont, and that was able to take care of this. But it was still a challenge to make this diagram just because of all the crazy behavior.
So in principle, that means you would have need a better computer, more computational power.
Yeah, maybe some more computational power, and maybe I wasn't using XPP to its full power.
Okay, thanks.
Thanks, Andreas. Well, I shouldn't really ask you any questions, Adam, so I'll refrain. And if nobody else is coming in, then we'll say thanks again. Nice presentation. And we can move on to the next speaker.